Okay, ladies and gentlemen, let's continue with chapter 8 on internal forced convection. We are making use of the textbook of Cengel and Ghajar, Heat and Mass Transfer. And it's not the first lecture of this chapter. We've already done 4 parts out of this chapter. The first one was an introduction. Then paragraph 8.2 was the average velocity and temperature. 8.3, the entrance region, and then 8.4 is what I've done with you previously. And I've emphasized how important it is. There are 2, let's call it extreme cases, not extreme, but 2 typical cases which are being used in industry, which is called the case of constant wall temperature and the case of constant heat flux. And depending on which one of these 2 cases it is, you can know what will happen on the inside, and we have derived appropriate equations. We're going to continue with that with paragraph 8.5, and for that I'm going to just quickly revise some of the work with a constant heat flux and the constant wall temperature. Okay. So in terms of just looking on the PowerPoint, just going back to some of the things that I've written on the board, the general thermal analysis, there are 2 possibilities. The one is the constant surface heat flux. If you can follow the mouse there, you'll see what is important is that the fluid temperature increases linearly. This is the part where the flow is still developing, and after the flow is fully developed, then that temperature difference there will be a constant. We can also make use then of, when we do a little bit of derivations, we can actually calculate the surface temperature as a function of the heat flux and the heat transfer coefficient. Then, the case of the constant surface temperature, we've discussed the issue of the temperature difference, because the problem is that in this case, the wall temperature is constant, and then the fluid temperature will do something like that. So getting a very good delta T is problematic. Okay, and equations were derived that can give us the outlet temperature as a function of inlet temperature, the heat transfer coefficient, etc. I've also discussed the very important concept of the NTUs of an heat exchanger. And we've looked at different values. And I've indicated to you that normally NTUs of 5 and larger should never be used. Okay. Why? Because if the NTU is equal to 5, then the outlet temperature is going to be approximately 99.5% than that of the wall temperature. And from a value of 3, the 3 is not in here, but between 3 and 5, just to get 1% more or 2% more, you will typically have to double the size of the heat exchanger, and that's very expensive. Laminar flowing tubes is the next part, and what is important to realize is now that from fluid mechanics, for laminar flow, I've showed to you, or we have showed to you, the velocity distribution. The velocity distribution gives us the pressure drop. Also, from the previous 2 analyses, we can now actually derive the temperature distributions, and we can do an energy balance around a control volume. And then firstly, before we get to that, just to as a little bit of a revision, you'll remember that for laminar flow through a tube, the friction factor is 64 divided by the Reynolds number. Okay? Do you remember that? So if you think of a Moody diagram as the friction factor as a function of Reynolds number, then That is the line for friction factor divided by 64 for laminar flow, and then we had the line here for a smooth tube, epsilon divided by d equal to 0, and then we had all the other values here depending on how the surface roughness increase. So this line is the friction factor divided by 64. Sorry, what am I writing? 64 divided by the Reynolds number. Okay, so the friction factor is 64 divided by the Reynolds number. The friction factor is important because we can write the pressure drop as a function of friction factor multiplied by L of D multiplied by L of D multiplied by rho, the average velocity squared divided by 2. What I wanted to show to you is that we can now use the same approach as for flow, where we've derived the friction factor and look at an energy balance of an element. And what can be done now is that for the case of a constant heat flux, so the heat flux is equal to a constant, can be derived that the Nusselt number is equal to 4.36. And for the case where the surface temperature is constant, the Nusselt number is equal to 3.67. However, what is very important to realize is what I've showed you previously of the Nusselt number as a function of Reynolds number, or even as a function of x divided by d. Let's rather plot it as x divided by d, like that. Then the Nusselt number is going to do something like that, 4.36, and that would be for the flow fully developed. So this value of 4.36 is when the flow is fully developed. And 3.67, that one there, also when it's fully developed, but for the wall temperature constant. Those two values we are going to use a lot. So for example, in the test or exam, I say you've got a heat exchanger, the flow is laminar, and I don't give you heat transfer coefficients or anything. If it's a circular tube, laminar, and you can see from the problem, and we are going to do an example just now, you can see from the example or the problem, it's a constant heat flux problem, then you should know the Nusselt number is 4.36. If the wall temperature is constant, then it should be 3.67. When will the wall temperature be constant? It will be cases where you've got evaporation or condensation on the outside. When will you have a constant heat flux? You'll have a constant heat flux where you've got electrical resistance heating or in a nuclear reactor. Those are the two cases where you've got a constant heat flux. Now those two values are important. However, the big however is that they are just valid for a circular tube, a round one. The other cases are available in literature. So here you can see, for example, for a rectangular, depending on the A or B value, if A divided by D is 1, which means it's a square, okay, then for a constant wall temperature, the Nusselt number would be 2.98, and for a constant heat flux, it would be 3.61, and the friction factor will be 56.92 divided by the Reynolds number. And other geometries like that can be found in literature. In the textbook, only a total of 4 geometries are given, some of them depending on the aspect ratio, but other types of geometries are typically also available in literature, or you can derive it from first principles. Okay. Right, now, what you will also see in your textbook is an equation for what is called the developing laminar flow in the entrance region. So this region here, equation for that. And you will see that first equation on the PowerPoint now starts with 3.67 plus. 3.67 plus. Do you see it? Okay. And this 3.66. Okay, 3.66 plus. So if you look at this equation, you will see that the longer the length becomes, the smaller this term will be. Okay, so if the length is very long, this term will be approximately equal to 0, which means that the Nusselt number is 3.66. Take note, and that is very important, this equation is not a specific value at a specific point there. Okay. It is the average over the total length. So you will always have something like that. And if the length of the heat exchanger or the tube is equal to that, then it means that this is the average over this total length. So it will be approximately that value H1. Okay, and that is very handy, because if it wasn't like that, it means that you will have to go and work it out at many different points, and you will have to do the integration yourself. If the total length of the heat exchanger is longer, okay, then it will be something like that. Then the average would be over the total length, and most probably the total length would have something like that, and that would be the average over that total length there. So that is the average H1, and that's the average H1 and H2, depending on the length L. So if you put the length L into that equation, together with the Prandtl number and the Reynolds number, whatever it should be, now the Reynolds and the Prandtl number, you can calculate the Nusselt number over the total length, and it gives you the average. So the fact that it's an average is very important. Okay, then there's another equation which also gives an equation, but now it gives a ratio with it, which is the viscosity of the bulk divided by the viscosity of the surface. And you will see that a lot. And usually that is being used when there's a huge temperature difference between the wall and the bulk. So normally very high heat fluxes. Then that term will be important. Now the question that many of you are going to have is, but when do I know? And the answer is, well, you just look at this ratio. If you look at this ratio of the viscosities, and they are close to each other, then that is going to be equal to 1. Okay? In any case. However, if this ratio becomes 0.8, 0.7 or something like that, and you've got 0.7 here to the power of 0.14, and you look at that and you see, well, that total is now 0.6 or 0.5, then obviously it is important, and you need to take into consideration the viscosity ratio. Okay, and then the last equation is now for where you have two parallel plates, and you want the Nusselt number. Now take a note that these Nusselt numbers are all for that are given here as for the specific case of the surface temperature constant. They are not in your textbook equations for the constant heat flux. Why? Because it hasn't been done yet. Okay. So it hasn't been done yet, they are not available yet. So they are not equations that we can use for that. Any questions? Let's do an example. The example that we're going to do is a case where we've got a tube with a diameter of 25 millimeters, and the average heat transfer coefficient is given as 800 watts per square meter degree Celsius. The inlet temperature is equal to 15. And the outlet temperature is equal to 115 degrees Celsius. So there's an increase of 100 degrees Celsius over this tube. Here on the outside, we've got steam, which are condensing. And this surface, it's condensing at 120 degrees Celsius. Let's rather write it like that, 120 degrees Celsius. The question is, how long must this tube be? How long must it be? Now, heat exchangers, we're going to address in the last paragraph of this module. And then we're going to look at different types of heat exchangers which are available. But normally, what you will have here is a shell and tube type of heat exchanger. Okay. And you will typically have steam coming in there, it will go out there. Okay. And inside here, you will have many different tubes. I'm going to schematically just show 3 of them. Okay. And the steam is typically going to enter here. It's going to be on the outside of the tubes. And in here we will have some baffles, like that. I've just shown 3 tubes here, but it can be hundreds of them. Okay. So the steam is going to be on the outside of the tubes, and it's going to flow around that, and it's going to flow out like there. Okay, so that's on the outside. On the inside, you can have water, which now flows through the tubes like that. And here's a header, and all this water is collected here, and maybe it goes out there. Okay, something like that. Okay. Now, if the steam is condensing here on the outside, then if you go and look on a TS diagram, condensation means that is a TS. It's going to typically start as a saturated vapor, and there it's going to be a liquid. However, what is important is that this is equal to HFG, and for steam at 120 degrees Celsius, this would be 2,203 joules per kilogram Kelvin. Okay. Therefore, what is sort of magic or special about the heat exchanger, where we have two-phase flow, is that when it starts to condense here on the outside, everything here is going to be gas, and it's going to change, and it's going to become more and more liquid until, if it is at that point here, everything is liquid. While that happens, the temperature remains constant. Okay? And that is a very important thing for us to work with if we design heat exchangers. If you can have one of the streams where the temperature do not change. So, and that you can only get with condensation and with boiling and evaporation. Okay. So this happens at 120. So if you imagine that tube now, which is being exposed to the steam, it will mean that the surface temperature everywhere is 120 degrees Celsius. You agree? So therefore, in terms of the previous paragraph in which I've mentioned to you how important it is that you must be able to distinguish between a constant wall temperature problem and a constant heat flux problem, this falls into the category of a constant wall temperature problem. Do you agree? So it is a constant wall temperature problem, or we are just going to use the notation Ts is equal to a constant in the future. Okay, now although this is going to happen with the steam, with the water is going to increase in temperature from 15 to 115. So some of you would say, but now this thing is going to be steam, because it's higher than 100. It depends on the pressure. If the pressure is high enough, typically if the pressure is atmospheric, yes, then that will be the case. But if the pressure of the water is 200 or 300 kilopascals, typically it will be if you pump it through it, then it's not going to be steam, it is still going to be water. Now we need the properties of the water, and for that we use the bulk temperature as we've discussed previously, and that is the inlet temperature and the outlet temperature divided by 2, which is equal to 65 degrees Celsius. So at a temperature of 65, you can go in your textbook and you can go and see that Cp is equal to 4187 joules per kilogram Kelvin. In terms of, many students typically would look at a problem like this, and then sometimes you immediately want to become too complicated, and you do not see before your eyes that actually you can calculate one of the most important things just by saying that the heat transfer rate is equal to the mass flow rate, the Cp, multiplied by the outlet temperature minus the inlet temperature. It is not always the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by delta T. We are going to use it, but we first need to get the heat transfer rate. Okay. And what I forgot to say is that, the mass flow rate is 0.3 kilograms per second. Okay. And it's water, and it's high pressure. So the water is one other high pressure. Right, so the heat transfer rate is equal to the mass flow rate, which is equal to 0.3. The Cp value is equal to 4187, multiplied by the outlet temperature is 115, minus the inlet temperature is 15, and the result is 125.6 kilowatts. So let's go and calculate then the length required. So the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by Ts minus T bulk. The heat transfer rate is 125.6 kilowatts. The average heat transfer coefficient was given as 800. The surface area of the tube is pi multiplied by 0.025 multiplied by L multiplied by the surface temperature is 125 minus the bulk temperature, which is 65. And if we calculate it, then we can get that the length of the tube required is 38 meters. Are you happy with that? Any questions? Okay, rubbish. Okay, why? Because, and that is why I said it is so important with the previous paragraph, that you always think of these two case studies. And the best advice I can give you is make a sketch. Okay. And with a sketch, you're going to have the surface temperature, which remains at 120 degrees Celsius. It's a constant wall temperature problem. The inlet temperature of the water is going to be 15. The outlet temperature is going to be 115. So there's 120. Okay. And the trap is that the water temperature doesn't do that. Okay. The water temperature does something like that. Okay. And we have now used the bulk temperature, which is there, as the temperature difference. The actual temperature difference is much less. So therefore, we've said that when you've got a constant wall temperature problem, you cannot use delta T. You have to use the LMTD, the log mean temperature difference. Okay, so now let's see what happens when we use the LMTD. Okay. Okay, so many students have problems with the LMTD. And the LMTD can be written as delta T at the inlet minus delta T at the outlet divided by the ln of delta T at the inlet divided by delta T of the outlet, and or different similar types of configurations. However, you can rather do it like this, and that's the method that I prefer, and that is why I say always make a sketch for yourself. This temperature difference is 120 minus 105. So this temperature difference is 105. Do you agree? This temperature difference here is 5. Okay. So the LMTD is always equal to that temperature, 105, this temperature minus that temperature, which is 5, divided by the ln of those two terms. Okay. This temperature difference is 105, okay, minus 5, that value there, the ln of those two terms. And if you go and calculate it, then that temperature difference is actually equal to 32.85 degrees Celsius. Now, we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied not by delta T, but delta T LMTD. The heat transfer rate is equal to 125.6 kilowatts. It's equal to the heat transfer coefficient multiplied by the surface area, pi multiplied by 25 millimeters, 1 inch, multiplied by L, multiplied by LMTD, which is 32.85. And the correct length is then equal to 61 meters. Okay. It's about double. Could have done this problem also differently. If you go back to the theory of a constant wall temperature, then the outlet temperature can also be written as the surface temperature minus the inlet temperature e to the minus NTUs, the number of transfer units. Now I think in your textbook it is not written as NTU, but I prefer to work with NTU because it really says something to me. Okay. So if we calculate, or the outlet temperature was given as 115, the surface temperature as 120, so minus 120 minus the inlet temperature is 15, e to the minus NTU, we can calculate the NTUs. And the NTUs is given as 3.045. Now, that is about 3. So it means that if the NTUs is equal to 3, then these two temperatures are very close to each other. But as I've shown to you previously in the table, if you want these temperatures, this temperature to increase to 119.9, you will have to double the length of the heat exchanger to get that extra 4 degrees Celsius. Okay, now the NTUs you can also write as the heat transfer coefficient multiplied by the surface area divided by m dot Cp is equal to 3.045. The heat transfer coefficient is 800. Pi multiplied by 0.025 multiplied by the length divided by the mass flow rate 0.3 divided by the Cp value 4187 is equal to 3.045, and fortunately if we calculate it we get 60.9 meters. Okay, so it's about the same answer and they should be the same. Okay, now what I want to do with this NTUs, I want to go and show to you what is the temperature going to really be at that point there. Okay? What is that temperature going to be? So if we look at the equations, it looks to us as if there's no equation that you can do it with. There's an equation that gives you the outlet temperature, but not the temperature as a function of x. Well, we can do it with like this. We can say at L equal to 60.87 divided by 2. So if we look at that, it means actually it is the NTU values of the NTU divided by 2. Because this equation is the heat transfer coefficient multiplied pi d multiplied by L divided by the mass flow rate Cp. So if we want to know, not at L, but at L divided by 2, it means it is just half of the NTUs. So if we make use of that, the NTUs of 3.045 divided by 2 is equal to the heat transfer coefficient multiplied by pi d multiplied by L2 divided by 2. Okay, sorry, no. I'm talking nonsense. So if we use 3.045 and we use this equation, the outlet temperature, not really the outlet temperature, but the temperature at L divided by 2 is equal to Ts minus Ti e to the minus NTUs divided by 2. So the temperature that we're going to calculate like that at half the NTUs will be that temperature. And that would be equal to 97.1 degrees Celsius. So if we go and put it in here, then that temperature would be 97.1. And that temperature would be 65. And that temperature would be 120. So now you can see why it is so important that you use the LMTD and not that temperature difference. If you use that temperature difference, it is not going to be correct. So you have to write down for yourself. And it is actually in your textbook. So if you look in your textbook on page 482, page 482, the last sentence before example 8.1. That last sentence says, therefore, we should always use the log mean temperature difference when determining the convection heat transfer in a tube whose surface is maintained at a constant temperature Ts. Okay, so what it says is if Ts is equal to constant, always use LMTD. Okay. So if we look at these cases and we look at delta T between the surface and bulk, okay, there's surface and there's bulk, then that is equal to 120 minus 65, which is equal to 55 degrees Celsius. And if we use delta TSM, okay, that one there, then it is 120 minus 97.1, which is equal to 22.9 degrees Celsius. Now do not get confused. Okay, this TSM that I'm referring to there is just that difference. That is not a true difference if you do a full integration. I'm just trying to show you the point in terms of where that temperature really is. The real temperature difference is 32.85. So if that is equal to 22, then 32 is going to be somewhere there, and therefore typically if you've done the integration, that would really be the true delta T between the wall and the steam. Do you follow, ladies and gentlemen? Okay. Okay, then the last part that I would like to show you in this chapter is the case for turbulent flowing tubes. And these are just a number of equations which are given in your textbook, and I'm not going to rewrite it on the board because they are there. It shows typically, firstly, the friction factor equation for a smooth tube. It comes from your fluid mechanics. Then it gives the Nusselt number as equal to 0.125 multiplied by the friction factor multiplied by Reynolds Prandtl to the third. And that is called the Chilton-Colburn analogy. Why? Because it gives the analogy between the friction factor and heat transfer. That is where that equation comes from. Then there's an equation which is known as the Colburn equation. The Colburn equation is the Nusselt number is equal to 0.023, Reynolds to the 0.8, Prandtl to the third. And it's valid between those boundaries. After that follows what is called the Dieters-Boulter equation. 0.023, Reynolds to the 0.8, Prandtl to the n. So very similar to that one, where n is 0.4 for heating and 0.3 for cooling. And then an equation, if there's large variation in the properties, there you can see what I've referred to you previously, the viscosity at the bulk and the viscosity at the surface. Okay? And then there's also an equation which is called the second Petikov equation, and then lastly the Glinsky equation. And then there are also equations for liquid metals, for a constant wall temperature and for a constant heat flux. Okay. Those are all for the turbulent flow regime. Now if you look at those equations, and I give you a problem to work out in the test or exam, then the challenge normally for students is which equations do you use? Well, the first thing I have to point out to you is that all these equations are plus or minus 20% in accuracy. So they are not that accurate, firstly. They have become more accurate with time, so it is considered that this equation of Glinsky is the most accurate of them all, but you will see it is much more work to calculate it than, for example, the one that I use mostly, which is the Dieters-Boulter one, which is the simplest one to use. Okay, so it depends on how much energy you have and how accurate you want to be in terms of calculation of getting the Nusselt number. But take note, all of them are a function of Reynolds number and Prandtl number, and some of them also a function then of the friction factor, taking into consideration the analogy between all these equations. Okay. Any questions on these equations? With the next lecture, we will do an example, or some more examples, so that it can be more clear to you. Thanks, Dan.